I've signed up to talk about foundations and implications of complexity. I've been working on complexity for about 45 years now, which seems like a long time to me, but I'm pleased to be in a situation where I started my career quite young, so I was often the youngest speaker at a conference by some 40 years or something. I thought that would never happen to me again. I'm very happy that this morning that's happened. All right, let's talk about complexity and what I see it as meaning, some of its foundations and implications. So I started off being involved in physics and being interested in how phenomena happen in the world. And if we look at kind of the history of science, I think we can break kind of the explanations of things in the world into a series of epochs. The first one, probably in antiquity, was the question of sort of what are things made of? How do we describe what things are made of? Are things made of atoms? Are things made of other kinds of things? What are things made of? Many fields of science are still in the stage of basically just describing what are things made of. Then, in the 1600s, a big sort of advance was this idea of kind of a formal description of how things worked, using in particular ideas from mathematics. The notion that it wasn't just a question of what things were made of, it was a question of what a formal theory of what those things might be, something that could be described using mathematical equations. And the whole approach of using mathematical equations became sort of a defining feature of exact science. It was very successful in studying celestial mechanics, in studying all sorts of things which have led to modern engineering. And so by some time when I got involved in these things in the late 1970s, early 1980s, in a sense, exact science was almost defined by being something about which there could be mathematical equations. So the question that I got interested in was, okay, we see in the natural world all of these complex phenomena. How can we explain them? Can we, for example, write down mathematical equations which describe these phenomena? Well, I tried to do that, didn't work very well. I knew all these fancy methods from theoretical physics, tried to apply them to these complex phenomena. They didn't really seem to apply. So the question then was, well, what else could one do? If one's going to make a theory for things, how can one base one's theory if it isn't on mathematical equations? That had been the tradition for 300 years to do that. So I thought, what if one is going to have a theory of things, it better be the case that the things one is describing are ultimately governed by some kind of underlying rules. What might those rules be like? In mathematical equations, we have particular rules with derivatives and integrals and all kinds of things from mathematics. What is the sort of general case of describing things by rules? And conveniently, in our times, there is a paradigm for thinking about those things, and it's computation. When we think about computer programs, we're thinking about a way of specifying what will happen by giving a series of rules. When we write computer programs, we tend to be used to writing programs where we imagine the purpose of the program and we write down individual pieces of the program specifically to engineer it for a particular purpose. But what I got interested in the early 1980s was the question of, well, what if one generalized from mathematical equations and said the natural world could use any of those rules which corresponded to computer programs, and then what kinds of programs might the natural world be using? And so that led to a basic science question, which is, if you just look at programs, you pick programs at random, and you ask, what do they do? What will the results of that be? And this is a field of science that I think in many ways is sort of, perhaps one could even argue, the most fundamental field of science. I'll talk perhaps a bit about how it sort of underlies even the things that we think about the foundations of mathematics and so on. But this idea of just pick rules and see what they do, it's a field I now tend to call ruleology. Okay, so what happens if we do that? Well, here, let me just, one of the nice things about modern times is that, so yeah, we can see it, good. We can do everything in real time. So if I were to, let's talk about a particular kind of rule that I've studied a lot. These are things called cellular automata, and they have a very simple way of being set up. It's just a line of cells. Each cell is either black or white. And then what happens is, as you go in a series of steps, the color of a cell is determined by the color of the cell immediately above it and to its left and right. So this is a particular rule that says what the color of the cell underneath should be based on the colors of the cells above it. So now we can ask the question, okay, what happens if we just run this rule for a little while? We can just say, let's just do that. Let's start it off from a single black cell here. Let's run it for, I don't know, 40 steps or something. What we get is something very simple. We start off from a single black cell, and with this particular rule, all we get is a simple pattern. So we had a simple rule, we get simple behavior. Let's try a different rule. Let's say we use this rule here. Let's change this here. Okay, again, a simple rule, simple behavior. We might think, our intuition might be, if the rule is sufficiently simple, the behavior must always be somehow correspondingly simple. Let's try another rule. Okay, this one is, again, very simple rule. But what it produces is a pattern that's a little bit more elaborate, more intricate. Eventually, it makes a nested fractal pattern. Okay, so one thing one can then ask is one can kind of go out in this kind of computational universe of possible programs, and one can ask what is out there, what possible behaviors can occur. And it's kind of fun to sort of redo an experiment that I did many years ago now. And just look at all possible rules of a particular kind. We're just looking at all possible rules that are set up with black and white cells in this way. So let's look at, let's say, the first 64 of them. Here they are. So each one of those pictures corresponds to a different rule for determining what will happen. In a sense, a different rule for an artificial universe, so to speak. So most of the time, it's true that one's intuition is right. A simple rule produces simple behavior. Keep going a little bit longer. And then we get Rule 30, my all-time favorite science discovery, this thing here. Let's look at a bigger version of this. Let's say we run Rule 30, let's say for 400 steps. I'll show you what Rule 30 is here. There's the rule. This is what it does. So to me, this is a very remarkable thing, because you might say, well, simple rule will get simple behavior. Our experience in doing engineering is that if we want to make something complicated, we have to go to a lot of trouble, we have to have complicated plans, we have to set the thing up in a complicated way. But here what we're getting is this extremely simple rule. We just started off from one black cell there, produces this pattern that looks very complicated. It has a certain amount of regularity over on the left. But for example, if we trace the center cells in this pattern, we'll find that for all practical purposes, they seem to us completely random. So this is sort of a remarkable phenomenon, that even though the rules can be simple, the behavior that's generated is very complicated. And what does this mean? Well, it sort of breaks out of the intuition that we've had that's been the intuition that we get from our engineering, our other kinds of activities. It tells us that actually out in this computational universe of possible programs, it's actually very easy to get a great deal of complexity. And the thing that to me was very exciting about this is I think this is kind of the secret that nature uses to make all the complexity that we see. It's at least, well, most of the complexity that we see. We'll talk about that a bit more later. So that in this sort of computational universe of programs, it's easy to get programs where even though the program is simple, the behavior will be complicated. And we can go and look at all sorts of different particular examples of this playing out in different kinds of systems in nature where this occurs. Okay, so what's the significance of this for science in general? One thing one might ask is, one of the things that's sort of a triumph of the equation-based science of the 1600s and so on, is this idea that you can kind of computationally reduce one's understanding of a system. So, for example, you're studying the motion of planets or something, and you're asking, where will the Earth be 1 million years from now as it orbits around some idealized sun? Well, you could trace those million orbits and just see orbit by orbit what happens, but we know we can just make a formula into which we plug the number 1 million and we get the answer. In other words, we've been able to come up with a computationally reduced way to describe how the system behaves. We don't have to follow every step to see what happens. Question is that a general thing? Is this idea of prediction, this idea of us being able to kind of jump ahead and computationally reduce what has to be done, is that a general feature of science, or is that something particular to the science that happened to emerge from what was done with mathematics in the 1600s? I think it is not a general feature of science. And for example, this Rule 30 cellular automaton system is almost certainly an example of a phenomenon I call computational irreducibility. If you want to know what is going to happen, a very large number of steps in the future, you can clearly find that out by just explicitly evolving the system and seeing what it does. The question is, can you jump ahead? Can you, the human scientist, be somehow smarter than the system and be able to jump ahead and see what it will do without having to trace each step to see explicitly what happens? Well, this phenomenon of computational irreducibility is a consequence of kind of a fundamental principle that I think is a very useful principle for understanding a lot of things about the world. It's a thing I call the principle of computational equivalence. So when you look at some phenomenon like this, any process in nature, and you say it's following rules, it's generating some output, one thing in modern times that we can think about is that this process is effectively performing a computation. It's been given some input, it's given some computational rules, it will generate some output. So one of the questions is, if we look at all these different computations done by systems like Rule 30, done by systems in nature, how do these computations compare? Are some computations more sophisticated than others? How does that work? Well, one of the things that was discovered in the 1920s, 1930s is the idea of universal computation, the idea that there exist particular systems that have the property that if you feed them appropriate initial conditions, initial data, they can do any computation that any system can do. That idea has been tremendously important in technology. It's what makes software possible. It's basically what's made the whole computer revolution possible. But that idea also has significance in science. And I think one of the things what the question then is this phenomenon that you can find systems that have this property of universality and so on, is that something very special? Do we have to go and build a special CPU chip to be able to get a universal computer or not? The principle of computational equivalence says that actually there isn't, that in a sense, computational sophistication is ubiquitous. Above some very low threshold, essentially every system you look at that is not obviously simple in its behavior will be equivalent in its computational sophistication. So one consequence of that is that lots of systems in nature will be computationally universal. Has another consequence, which is the phenomenon of computational irreducibility. Why does that happen? Well, what would we be doing if we say, okay, this Rule 30 system, it goes through 1 million steps to work out what it's going to do, but we can be cleverer than it. We can figure out in some computationally reduced way what's going to happen. Well, for us to be cleverer than it, we in a sense have to be computationally more sophisticated than it is. But this principle of computational equivalence says that all these different systems in the world, whether they're these Rule 30 systems or our brains or whatever, are all computationally equivalent. So in a sense, we can never systematically win the competition of us being able to work out what's going to happen faster than it happens. Now you might say, so one thing that means is there are limitations to science. There are things that the traditional science of the 1600s and so on, mathematical science, will not be able to capture. There are things where we won't know what's going to happen other than by essentially running the system and seeing what happens. You might say, so that's a significant thing for science because it's a way in which there's a fundamental limitation on science that is emerging from within science. But it's, in a sense, it's for us, I suppose, in living our lives, it's kind of a good thing because it's kind of what gives us the idea that sort of the passage of time is significant. If it was the case that we could just say, oh, we know what the outcome of all of this passage of time that we go through is, the answer is 42 or something, then there would be sort of nothing achieved by the passage of time. What computational irreducibility implies is that there is something sort of fundamentally achieved by the passage of time. There is some computational process which is building up over the course of time. Okay, so just to sort of outline the this sort of idea of the sort of periods of the development of science. You know, in antiquity we have kind of a structural description of things. In the 1600s we have this kind of mathematical description of things. Now we have this kind of computational description of things. One thing that differs in those descriptions is the role of time. In the structural description, time isn't really involved. It's just what are things made of. In the mathematical description, time exists, but it's kind of just a variable. You can just turn a knob and say, I want to get the answer at any time in the future. By the time we're dealing with the computational paradigm, time is something more significant. We can't work out what's going to happen in the future except by irreducibly going through these computational steps. So that's kind of a way to distinguish those three periods and to understand that there are things that will not be achievable by science in this sort of third period of computation because of computational irreducibility. So you might say that's kind of a downer. That means that there are sort of limitations on what one can do in science. One of the things that has emerged in the last few years, for me at least, is a realization that there's another level, there's a sort of fourth epoch in the development of theoretical science, which actually recovers some of what we lost in computational irreducibility. So let me talk a little bit about that. So a thing I was long interested in is the question other people have been interested in also of kind of what might there be a fundamental theory of physics? Might there be kind of a fundamental underlying structure to the physical world? And the question is, once you've seen things like Rule 30, you start wondering, could it be the case that everything we see in the physical world could similarly come from some simple computational rule just being run out for a long period of time and making everything that we see in the universe? Could that be the case? What might that rule be like? Well, it turns out that it can absolutely be the case, and I think we now know, kind of at least an outline, what that rule is like, and I can describe that a little bit. Let me just show you something here. Maybe, okay. Oh, you can see that. So, this is to me, very remarkable breakthrough that we had in 2020 in trying to understand sort of what is underneath everything that exists in physics. And people have wondered for a long time, is there a bottom level to what you can work out in physics? I think now we strongly believe that there is, and we know what it's like. And what's interesting is how that interfaces with kind of this notion of computational irreducibility. Maybe I should actually, okay, so let me try and describe this. So the first question, which is sort of a foundational one, is kind of what is the universe made of? And the thing that is most obvious about the universe is there's space in the universe. And people have thought since Euclid and so on, space isn't made of anything. It's just something you put things in and you place them at certain positions and so on. Well, we've learnt that lots of other stuff is made of things. We've learnt that materials are made of atoms. We've learnt that light is made of photons and so on. But still we think that space is just a thing that isn't made of anything. I think that's not correct. I think space is made of things. You can think of them as kind of atoms of space, these underlying elements that make up our physical universe. What can we say about these elements? Practically nothing. We can say only that an element exists and that it's distinct from other elements. And we say then that what we specify about these elements is how they're related. One element is related to other elements. So we have this giant collection of these elements and relations between elements. We can think about that as some kind of graph or hypergraph. And that hypergraph is a representation of sort of everything that exists in the universe, the structure of space and the contents of space as well. And we can think about sort of the content of space, electrons and particles or whatever else. It's a little bit like what happens in a fluid like water. At the lowest level, they're just a bunch of molecules. But when we see things like vortices in the water, those are made from sort of the collective motion of lots of molecules. And so it is, I think, with space that things like electrons are made from kind of the structure of the particular structures in this hypergraph that represents the universe. So in any case, the thing that, and there are many features. So when we look at, for example, fluid dynamics, and we start off from the molecules, we know that from all these molecules bouncing around, we can derive the equations of fluid mechanics as the kind of large-scale limit of what happens with all these individual molecules. The corresponding thing that happens in space is that we derive Einstein's equations for the structure of space-time and for gravity. That's the similar thing that happens from these processes with these hypergraphs. time in this model is something very distinct from space. It is the progressive computational rewriting of this hypergraph using rules that are, well, they're not the same as the rules for a cellular automaton, but it's the same kind of idea. You're just taking a piece of hypergraph and rewriting it to some other piece of hypergraph, and you keep doing that. It turns out that the mathematics works out so that all the expectations of relativity theory and the correspondences between space and time all emerge as a large-scale feature of this system. Okay, so it turns out that we can ask the question, what's actually happening in the system? At the lowest level, all these atoms of space are doing very complicated things. They're sort of interacting with each other in effect through this hypergraph. And the process that's going on there is one that shows lots of computational irreducibility. If we were down at the level of atoms of space, we would have no idea what was going on in the universe. The only way we'd be able to work out what happens is by just following what the universe does. But the critical thing is that we are not operating down at the level of individual atoms of space. We, as observers of this universe, are operating on a much larger scale, and we have many limitations in what we can observe about the universe. So in a sense, all this activity is happening down at the level of atoms of space, but we are looking only at some very aggregated version of that activity. And it turns out that the aggregated version that we see has the feature that it shows what corresponds to continuum space and so on. There's a simple analogy. Let's go back to talking about molecules and things like gases and fluids and so on. If you're down at the level of individual molecules, you see all kinds of complicated behavior happening. When you look at a larger scale, you average that out, and you see something which might correspond to something like a continuum fluid. So, for example, one of the big results of looking at what happens at the level of molecules is the second law of thermodynamics, the law of entropy increase, and so on. And that law is basically a consequence of the fact that we are observing what happens at the level of molecules. We're observing it as large-scale observers. We're not able to trace what happens at the level of individual molecules. In essence, what happens at the level of individual molecules is computationally irreducible, but we just get to see kind of an aggregated version of what's going on. We are kind of computationally bounded observers. And as computationally bounded observers, we can only observe certain aspects of what happens in the system. And it turns out that for a computationally bounded observer, it is inevitable that when there is computational irreducibility, the second law of thermodynamics will be valid. So in that case. Turns out, in the case of space-time, the very same thing happens. If you are a computationally bounded observer, and you have one more condition. The other condition is you're an observer who believes that they are persistent in time, which is not an obvious thing, because once you have an observer that is part of the universe, it's made from atoms of space like everything else, at every moment, the atoms in space of which the observer is made will be new atoms of space. The observer will be recreated at every moment in time. So it's not a trivial fact that the observer has the impression that they are following a consistent thread of history. But if you have that impression and you are computationally bounded, then it turns out to follow that as a result of computational irreducibility of the underlying system, that is inevitable that you get the Einstein equations and you get the standard theory for space-time, which I consider very remarkable. More than that, you can go on and think about quantum mechanics. In quantum mechanics, what's important is that these rewritings of this hypergraph, there isn't just one possible path of rewriting. There's a whole, we call it a multi-way system of many possible paths and joinings of this of rewriting of the system, and that leads to sort of many possible histories for the universe. Well, the thing that is a complicated thing to think about is that we are observers embedded in that branching and merging universe. And so in a sense, the story of what we observe becomes a story of what does a branching brain observe about a branching universe. And it turns out again that if that branching brain is computationally bounded and believes that there's a single thread of history, then it inevitably follows that system must satisfy the standard laws of quantum mechanics. So it's kind of a remarkable thing because it means that it becomes possible to think about kind of deriving sort of basic physics, not as a matter of just the universe happens to work this way, but as a matter of something that is inevitable given the way that we are as observers of the system. I might say that that we're descending into more and more sophisticated concepts, but the ultimate concept here is a thing that I call the Ruliad, which is a thing where when we're talking about something like the evolution of the universe and we say it follows a particular rule, you might say, well, which rule is it? And you might imagine a very strange situation, a sort of a Copernicus-like situation where you say, we found the rule for the universe, it's this particular one here. And then people will wonder, well, why isn't it one of these other many, many possibilities for rules? Why did we get this special rule? Well, what I think is the case is that in some sense the universe is running all possible rules. That there's this thing I call the Ruliad, which is something where you're effectively running all possible computational systems, and you're running them, you're running each, imagine you have something like Turing machines, simple model of computation, you run all possible Turing machines from all possible initial conditions, you run it for an infinite time, you get this very complicated structure which involves things that branch from one Turing machine, ends up with two different states, those two states might merge together with different rules and so on. You get this very complicated structure. We are embedded in this structure. We are observers that are part of this structure. So everything that we experience is something that's based on kind of our way of parsing the structure, our particular slice taken from the structure. And so then the big result is that if we parse that structure, if we are observers who have these properties of computational boundedness and belief in persistence in time, then it follows that the way that we observe that structure inevitably must be one where we end up following these laws of physics that I've described. So I consider that an exciting thing because it allows us to kind of derive the fundamental laws of physics from something which is kind of a necessary structure that doesn't introduce any kind of anything where we sort of have a contingent fact about the world. I could go on and talk about how this Ruliad object also underlies mathematics. It represents all possible mathematical axiom systems. And you can also think about an observer of a system, just as we talk about the observer in physics as having these attributes where the observer in physics is parsing out these particular features of the physical world. So similarly, there's a mathematical observer who parses out certain features of this mathematical world to conclude things that are like the mathematics that we know. Okay, why is this relevant to complexity? The fundamental reason is that this phenomenon of computational irreducibility is a ubiquitous phenomenon. All sorts of systems will exhibit it. You might think that computational irreducibility would sort of mean it's the end of a certain kind of science. It's the end of being able to say much about what happens. But it isn't, because it turns out that even in the presence of lots of computational irreducibility, for an observer with certain characteristics, the observer is kind of sampling only those parts of the system for which there is predictability to be had. So in other words, one's turned the question of why, if we think about things starting from this Ruliad object, what's happening is different possible observers are sampling the Ruliad in different ways and concluding different things about what the kind of laws of the universe for them might be. And the point is that there are definite and reducible laws. There are essentially slices of reducibility that can be found in this otherwise irreducible system. What are the implications of that? Well, this underlying structure of the Ruliad is, I think, a very general thing. And all sorts of different fields, whether it's molecular biology, whether it's economics, whether it's other kinds of things, I think we can see as being derived from the Ruliad, but by a different kind of observer. So for each different kind of field, there's a different type of observer, a different set of features that we can observe. And it is then a consequence of the features that we observe, what kinds of laws we get. So for example, let's say economics. It could be the case that there's a type of economic observer who observes quite simple laws, even though the underlying system behaves in an irreducible way. Those laws might turn out to be of human use, they might not. They might be laws that are irrelevant. They're things that they might talk about things that we humans don't care about. The fact is that in physics, there's this, what's happened is that the things that we sort of sense and care about are things that correspond to slices of reducibility in the Rulliad, and that's kind of the alignment of observers like us exist in a way so that there is predictability for the things that we care about. Okay, mention one more thing. So I said I would get to sort of current times. One of the things that there's this, I actually should say another thing. I mean, in this kind of ranking of different epochs of scientific history, I think the thing that we have now reached is what I call multi-computational paradigm. It's kind of the fourth level after the computational paradigm, where we have this notion of time as this thing that progresses as a matter of computation being executed. So in this multi-computational paradigm, we end up with a situation where there are many possible paths for time. And that has the feature that the only way one can make sense of what's going on is by having an observer. The observer is a necessary feature of the system. There's nothing one can conclude without an observer. And so in this multi-computational paradigm, it's kind of one's reached another level, and one can think about it in terms of the different treatment of time. Now there's not just a single thread of time, there are many possible threads of time, but then we have to make sense of things with an observer. Once we have an observer, we then end up being able to make conclusions which are conclusions which involve computational reducibility. Well, okay, so we can think about kind of all of this. There's this kind of ocean of computational possibility that's out there, in which, for example, computational irreducibility is a common phenomenon. And the question is, we humans, much of what is out there in this sort of ocean of computational possibility, you know, I don't know, we can make some picture of what happens out there. The question is, do we humans care about this? And the thing is that what we have reached, as we can think about this as exploring the Rulliad, that we exist at some point in the Rulliad, and that we are exploring kind of the structure of what's possible around that area of the Rulliad. And the things certain things that we know we care about. There's certain things that are relevant to our senses. There's certain things that are relevant to the technology we build, and so on. And there are other things where we look at it and we say, well, that's nice, but we don't care. That doesn't connect to anything that we do. So one of the things I've been long interested in is there's all this sort of ocean of possibility of what is computationally possible. How does that connect to what we humans think about? I've spent a large part of my life building computational language, called Wolfram language, that is an attempt to capture kind of what we humans care about, a way to represent what we humans care about as a computational language. It's kind of the analog. Back 500 years ago, sort of the big thing that happened was the invention of mathematical notation that allowed people to sort of talk in a streamlined way about mathematical ideas. And that led to the mathematical sciences and calculus and all those kinds of things. What I've been trying to do for many years is, and happily many people use what we've built around the world, what I've been trying to do is to build a computational language which is kind of a notation for computation as mathematical notation is a notation for mathematics. And this computational language a big part of it is representing things in the world that we care about, whether it's cities, whether it's certain kinds of algorithms, processes, and so on, having representations for those things. Much as in a human language, we make up words for things that we care about. We make up a word for chair. We make up a word for website or something. We make up words for things out there in the world of possibilities. There are certain things that we care about. We give those words in our language. And in our computational language, the idea is to do the same thing, to describe the world computationally by essentially finding those words, those pieces of computational description. Okay, so just so there's this sort of what's out there that's computationally possible. There's what we care about as humans. One of the things that's sort of a thing of recent times is the world of things like ChatGPT, and we've been involved in machine learning and AI and things for a long time. So ChatGPT was a big surprise to everybody, including the people who built it. Nobody thought it was going to work this well. And the question is, let's see if I can find a picture here. Let's see. Here we go. Let's talk about, okay, here's a good one. The question is, what do we learn? How does ChatGPT relate to all these questions about complexity? What does ChatGPT do? What ChatGPT does is it has one task. You give it a piece of text, and it will try and continue that text in a way that's reasonable based on all the text that it's seen from the web and a bunch of books. So in other words, it's trying to statistically continue what it saw so far based on probabilities that it derived from looking at a corpus of about 4 billion web pages and a few million books and things like this. So it's trying to continue in a way that is sort of typical of what us humans have put on the web. So it's capturing what and it turns out, so it's got about 1 trillion words of sample human output. That's a decent fraction of all the output that is publicly accessible from our species, so to speak, as text. It's got those words. Inside it, it's essentially having to make a model for how to predict what the next word will be based on what it knows is out there in those 1 trillion words. And the model it makes is using an idea that comes from the 1940s, the idea of neural nets, a simple idealization of how brains work. And the neural nets, it's just, here are some examples of kind of trained neural nets. This is something where you're trying to get it to reproduce some function here where the value is yellow when it's in this region, red when it's in this region, and so on. And these are the best. What you're doing is you're feeding in the x and y coordinates here, and these are just working out with the weights corresponding to the colors and so on, and a little threshold at every node. You're working out what the output will be. What will be the output color here? And it turns out that you can take those 1 trillion words on the web and you can find out, you can figure out a neural net that's really quite good at predicting what the next word should be. It has about 175 billion connections in it. And which is comparable to the number of words that it saw, and that seems to be not a surprise, but nobody really understands quite why. So what we're seeing is that we've got this thing that is really like a cellular automaton, like many of these other systems. It's ultimately built of extremely simple components. It's just built of these simple artificial neurons. It happens to be a few million of them with 175 billion connections between them, but fundamentally they're simple underlying components. And the thing which is a huge surprise is that a system like that can actually produce text that is very human-like text. And so the question is, why does that happen? And I think the answer is because actually producing human-like text is not as complicated as one thought. In other words, we imagine that sort of language is this sort of pinnacle of the operation of intelligence and so on. It's something very general. It's actually something that I think is fairly specific. And I think what we see is that what ChatGPT has basically discovered is something which is a sort of direct follow-on to what Aristotle was working on a long time ago. It's kind of regularities of the structure of meaning that we don't happen to know about. So I'll give you an example. So one thing that ChatGPT does is it implicitly learns, let's see if I have a picture of that, it implicitly learns the grammar of English, the syntactic grammar of English. It was never explicitly taught how to parse an English sentence into nouns and verbs and so on, but it implicitly learns them. If you try and teach it, for example, something like a parenthesis language, a very simple language where you open and close parentheses, it will actually eventually fail to do this. It's not, and what's happening is that what ChatGPT is doing is it's doing essentially shallow computations. It's doing computations that are, well, okay, to explain in terms of computational irreducibility, one thing that it cannot do is irreducible computations. What happens when it runs is every new word it produces by just trickling through this neural net a series of numbers and figuring out what the probabilities of the next word are. It never gets to even have a feedback loop. The only feedback loop it has is through adding a new word, then looking at all the words it's had so far when it adds the next word and so on. So that means that all these processes that we've talked about in nature and so on that involve computational irreducibility, it doesn't get to do those things. So the surprise is that all this stuff that we thought was really complicated that has to do with how human language works doesn't involve computational irreducibility. Nature involves plenty of computational irreducibility, but in what we do when we make human language, we've taken a slice through things that involves only fairly shallow computationally reducible stuff. And what you can ask is, well, how did we, what are some analogies to how that works? And I think, let's see, I had a nice picture here somewhere. Yeah, that's a picture of the sort of the insides of ChatGPT, of some of its, sort of what it learnt, and somewhere in there, that's sort of a representation of the regularities of human language and so on, and the way that we think about things. But the thing that the thing to understand is it's generating language, and the question is sort of what are the rules by which it generates language? And there are two basic known kinds of rules. One is the rules of syntax, of grammatical syntax and so on. Those are rules which it has implicitly learnt. Another type of rule is something like rules of logic. And if we imagine, what was Aristotle doing back, a couple of thousand years ago, one way to think about what he was doing was he was looking at examples of rhetoric, of speeches people gave and so on, and he was asking what kinds of structures were repeated in those speeches. So, there might be, all men are mortal, Socrates is a man, therefore Socrates is mortal. That structure without Socrates and mortality is repeated over and over again, and that structure is what Aristotle identified as syllogistic logic. And so, in other words, there's this structure of meaning that is found repeatedly. And so I think what's happening in ChatGPT is that it's basically finding generalizations of logic that are other sort of structures of meaning that exist in human language, which Aristotle actually started looking for, but very few people have looked for them since. And we're actually sort of in a unique position to find these things because of understanding about computational language, having the example of ChatGPT and so on. But so what it means is that what it's really doing is there is some sort of semantic grammar of language which represents not just the syntactic structure, but also something about the meaning of language. And what's happening is that it's managing to piece together things which sort of fit together as puzzle pieces of semantically, things that are valid according to the semantic grammar, and that's kind of what it's generating. So, okay, so that's just an example of, well, what's interesting is that it's another case where we humans have managed to find this slice of the world that doesn't involve deep computational irreducibility. By the way, when if you use ChatGPT, you'll find out, if you ask it to do math problems or something, it will confidently tell you an answer, and the answer will be completely wrong usually. As you may know, we have this system called Wolfram Alpha, which takes natural language and does math problems by a very different method. It turns the natural language into our computational language. Then it uses kind of actual computation, which involves irreducibility and so on, to work out the answer. And of course, one can think about, and more than just think about, connecting, ChatGPT to Wolfram Alpha so that it can use tools, just like we humans use tools to do things like mathematical computation. It will be able to use tools too to be able to do that. But on its own, and the thing where it's representing what we seem to have in language and so on, seems to be, again, one of these things where we have taken sort of a shallow slice through all computational possibilities. So, okay, I should probably wrap up here. And I think the thing that I sort of most wanted to communicate was a few basic points. First, this discovery, this fact that in the computational world, unlike in the world that we are used to from doing engineering, or for example, from doing sort of mathematics, most kinds of mathematics, in the computational world, it's extremely common to have very simple underlying rules producing very complex behavior. that that's a generic thing, that generic thing is a consequence of a deeper principle, this principle of computational equivalence. The principle of computational equivalence has all sorts of implications in both science and philosophy and other areas, but it is the thing that is the cause that we can think of as the reason that it is that we see the complexity we see is because there is that principle at work. So that's, therefore, the presence of computational irreducibility then provides this limitation to the kind of prediction in science that we've been familiar with for the last 300 years. It's something where right now most of the technology we build is technology that assumes that we kind of understand how all the pieces work inside. And that's something that is the sort of is before computational irreducibility. Once you are dealing with computational irreducibility, you cannot expect to understand how all the pieces work inside. And in fact, if you ever want to use computation to its fullest extent, with its a maximally powerful way, then inevitably you won't understand what's going on inside because you have to have irreducible computation. And that applies to AIs, it applies to all sorts of other kinds of systems, that if you want it, you have this trade-off. You can either say, I'm going to understand what's going on inside, or you can say, I'm going to let the computation be as powerful as it can be, in which case you have computational irreducibility, and you have this limitation on prediction, and on sort of science-style prediction. But so, in any case, there's this sort of fundamental limitation, and that fundamental limitation makes one sort of start thinking about things in a slightly different way. You know, we think about what happens when AIs are doing everything in the world, and you know, we don't understand what's going on inside the AIs. And if the AIs are doing serious computation, we won't understand what's going on inside the AIs. What is that like? Actually, we have a lot of experience with that, because that's like our relationship with nature. Nature also is full of computational irreducibility, and we are just sampling pieces of what's going on. So in any case, the fundamental idea of computational irreducibility, these limitations on the kinds of things that we can say and that we can predict, the ways in which we can sort of be superior, to what happens in the natural world or the computational world. And then the final piece is this piece about the multi-computational paradigm, this idea of observers, this idea that observers like us can take slices of what's happening and have those show computational reducibility. And the science that we've done, we can think of it as we kind of expand in this Rouliad, we can think about points in the Rouliad corresponding to different kinds of ways that we can observe what's going on. And as we kind of expand our technology and our scientific paradigms, we get to sort of expand our domain in the Rouliad. Just like we expand our domain in physical space by sending out spacecraft, we expand our domain in the Rouliad by discovering more scientific paradigms and so on. And I think that process of that process is a never-ending process. It's rather easy to show that we will never run out of possible slices of computational reducibility. So there will always be places where we can make sort of scientific progress. We'll never run out of that, but there'll also be lots of things about which we cannot make kind of the types of statements that we've been familiar with making. I just want to emphasize again that in fields like, let's say, economics and things like this, I fully expect that the kinds of conclusions that we're able to make in physics we will be able to carry over those conclusions. We'll be able to talk about things like event horizons and black holes and gravity and so on in things like an economic setting, but with respect to a kind of observer that may or may not correspond to an observer that's useful for our purposes in the way that we experience economics. Anyway, I should stop there, so thank you very much.
Thank you, Stephen. I will ask you a question, so maybe
Please.
you can just sit down next to Edgar. Edgar wants something, which is his bottle of water. Why don't you sit down there, Stephen? I will ask you a question. Thank you, Stephen, for a very brilliant expose, matter of thought. Thank you, Stephen, for making my life very difficult, because now I have to rewrite entirely my lectures in history and philosophy of science. Thank you very much. I think there is a million questions that could be asked of you by the audience, but you are here for a while, so I think that people can just ambush you on the campus and ask you questions. En ce qui concerne la conférence très inspirante de Edgar Morin, encore une fois, vous pouvez poser des questions par écrit à Edgar Morin et nous allons le réinviter et il vous répondra donc aux questions que vous lui posez par écrit. Alors, maintenant, on va passer à l'inauguration du Luis Fresco Fund for Academic Mobility in Africa. Je crois qu'il y a, l'agence doit faire des manipulations, mettre une table là-bas, enfin des trucs assez compliqués. Je vous propose donc à ceux qui sont chargés de faire ces manipulations de le faire. Et I will abuse my position of Master of Ceremony to ask one question to Stephen. I don't see anything happening. Somebody is going to put the table. Yes, the table is coming behind you. Stephen, I have one question for you. I have actually a million questions, but one. You say that during the history of science, we used to see the world as a kind of the universe of the space as kind of receptacle, a box, right? For many times. Well, general relativity would not exactly think the same thing, but it's okay. However, you think that space is made of points, infinitely small points. Well, there used to be something called ether before Einstein, and Einstein disposed and dispatched the whole notion of ether. So, Mr. Wolfram, are you actually rediscovering ether? That's a question for you. And you have exactly 2 minutes, 30 seconds to answer.
Okay. You know, the ether has been back for a long time. In quantum field theory, there's an ether. The cosmic microwave background is like an ether. But the idea that space is made of something, that there is a, yes, it's as a matter of fact, there was a theory in the late 1800s that atoms were like vortices in the ether. This theory, I don't think it's not in detail correct, but this theory, we're back with a similar kind of thing. We're dealing with topological obstructions in a hypergraph, but it's the same kind of idea. So in a sense, the notion, the sort of pure mathematical notion, we just write down a formula and that describes how the world works, and there's nothing there, so to speak. This is not what I'm saying. There is something there, and the thing that's there is something very abstract. I mean, this is not when you say, for example, these points, they don't have a position. They define position, so to speak. All that one says about these points is how they are related to each other. So everything else must emerge from those relations. So yes, it is a nice and charming thing that it should be emphasized. One of the things people say about relativity is, that means that there is no absolute reference frame in the universe. Well, actually, for the last, 30, 40 years now, it's been known that the Earth is moving at 1,000th of the speed of light relative to the center of mass of the universe. There is a preferred reference frame. It's the preferred reference frame of the cosmic microwave background. So it's, these things which are kind of quick summaries of what these theories say don't always capture what's going on. And I think I happened to just be studying the history of thermodynamics. It's a fascinating history. Which I think I finally unraveled, and I'm like, why has nobody unraveled this before? The main reason is because people haven't known why the second law of thermodynamics is actually true, and so you can't go back and see. But that's anyway. You said a few seconds, and I took more than a few seconds. Yes, it's a good and interesting question, and it's a charming. It's the question of why people believed that space is not made of anything. It will be seen one day as one of those little glitches in the history of science. People were really close. I mean, Einstein, for example, in 1916, he wrote to somebody, said, in the end, we'll discover that space is discrete, just like matter, just like electromagnetic radiation. But he said, we do not yet have the mathematical tools necessary to see how this will work. 100 years later, we do.
All right. Thank you, Stephen. Thank you.